Thank you everybody for joining today. My name is EliasToon and I'm a candidate in the MSGIST program at the University of Arizona. Today will be my presentation titled Evaluation of Fine Particulate Matter Air Sensor Data and Interpolation Models in Phoenix, Arizona. So just as some background on what particulate matter is, particulate matter is a mixture of solid particles and liquid droplets. Those solid particles can be things such as combustion particles, organic compounds, or metallic compounds. In this graphic here, you'll see a depiction of the diameter of different small particles. And so in the bottom left-hand corner, you'll see a depiction of the size of fine beach sand, which is generally around 90 microns. You'll also see the thing going through the middle of the graphic is the width of a human hair, which is on average about 50 microns. You'll also see blue dots, which are depicting particulate matter of 10 microns or less. And then you'll see pink particles there, and those are inset on top of those blue particles. So even smaller, those are going to be fine particulate matter, or PM2.5, which are particles that are 2.5 microns or less in aerodynamic diameter. And these are the particles that are the subject of this presentation today. And these are particles that are regulated under by the EPA under the National Ambient Air Quality Standards as a criteria air pollutant. And exposure to PM2.5 has been linked through epidemiological studies to both chronic and acute exposure and negative health outcomes. And so some of those negative health outcomes are things such as increased rates of asthma, and has even been linked to things like mortality. So how do we measure exposure to PM2.5? So the nation has an ambient air quality monitoring network, which is operated by states, locals, and native nations. In 2022, there was 1,240 of these PM2.5 monitors located around the country. On the right-hand side, you'll see a depiction of what these equipments look like. So this is a federal reference monitor from Thermo Fisher. So rather large and expensive pieces of equipment. And the expense and the size and the quality of these instruments really limits their growth. They can only be deployed in so many locations with limited resources and funding and capacity to take care of them. On the left-hand side, you'll see a map that shows metropolitan Phoenix area with dots representing current air PM2.5 air monitors that are located in the area. I've also applied a 4-kilometer buffer scale around those just to show you what those monitors are supposed to be representative of. So you can see, even looking at this graph, even though there's quite a few PM2.5 monitors, they are inadequate to characterize the exposure of PM2.5 over an entire urban or metropolitan environment like Phoenix. So what are some opportunities that we could take to try to characterize PM2.5 exposure over a broader range? One option is use of air sensors. So air sensors are low cost. An example here is a purple air sensor, which will also be the subject of this presentation. These are on the order of $200 to $300 to get one of these sensors. And as of 2022, there was 12,000 PM2.5 purple air sensors represented on EPA's fire and smoke map, so almost 10 times as much as the nation's ambient air quality monitoring network. There are some issues with using air sensors. As you can probably guess from their size and their cost, they're not always quite as accurate. And so Barkjohn et al. In 2022 performed a study where they co-located these air sensors with air quality monitors to test to see if they were comparable. And what they found is that they're highly correlated, but they often had inaccurate values, often by a factor of 2 in comparison to the reference monitors. And so what they were able to do in that study was develop a correction formula, which is displayed here and is also used in this study. Another opportunity to characterize PM2.5 exposure outside just the ambient air quality monitoring network is through interpolation analyses. So interpolation analyses use a limited sample data set to predict values in between those points and create prediction surfaces. Some techniques that can be used are listed here, such as Kriging or inverse distance weighting, and those generally rely upon statistical methods for calculating those values in between the known points. So for this project, the study was aiming to evaluate the potential for combining those public purple air sensor data and using interpolation models to generate fine particulate matter concentration prediction surfaces for Phoenix, Arizona. So for this, 3 different data scenarios were analyzed. The first was using only data from the air monitors. The second was using a combination of adding the air monitoring data plus the uncorrected air sensor data. And the third data scenario was using the air monitoring data and the purple air sensor data after it had had the correction equation developed by Barkjohn et al. Applied to the data set. For the project study area, it was determined using the Bureau of Land Management's public land survey system. So you can see in this map here on the left-hand side, the small circular dots are going to represent air quality monitors. A grid was developed that was one township outside of the townships where air quality monitors were located to cast a wide net around those monitors. And purple air sensors, which are represented in triangles, where data was grabbed from those and included in those data sets as previously described. For the study period, it was performed over a 15-day period from December 17th, 2022 through December 31st, 2022. These days were selected because at the time of the study, 2022 is the most recent available quality assured data set from EPA. And this 15-day period is often correlated with very high and variable concentrations in the Phoenix metropolitan area due to influences from firework activity and residential wood combustion from fireplaces. For the project data, it was primarily downloaded from two locations. So the first was the air monitor data, which was grabbed from EPA through their air data website. So their pre-generated daily PM2.5 data was simply downloaded and then filtered to the location and the date for the specific monitors. The air sensor data was a bit harder to obtain. It required the use of the Purple Air Data Download Tool program and use of their API. So that involved the creation of an account, generation of API keys, building a lat-long bounding box to query the sensor locations, downloading hourly data as opposed to daily data in UTC time, converting that to local time, and then generating those 24-hour values and filtering by the date, and then applying the Barkjohn et al. Correction equation. So at the end of that, I had the data for the 15 days. For 2022, and these are the 8 steps that we went through to complete the project, all the way from data preparation through the end, which is the animation of the map series. On the second line there, you'll see the methods. The methods that were used were a combination of using ArcGIS Pro Model Builder, as well as various manual geoprocessing tools, and even Adobe Photoshop. So diving into the methods, the first step was I developed a model to prepare the data. And so this took all of the data that was previously in one Excel file. It brought it into a table in ArcGIS. It spatially referenced that data, projected it to an appropriate projection method, and then it split the file from just one into daily model input files and stored them in a featured data set. So the output of this was those 15 daily files. The next is I wanted to know what interpolation method was the best performing to compare all 3 methods across. And so I also built an exploratory interpolation model, which took those 15 daily files and iterated over each of them and ran the exploratory interpolation geoprocessing tool 3 different times, one for the EPA dataset, one for the uncorrected air sensors dataset, and then lastly for the corrected air sensor dataset. I'll discuss the results a little bit later in the results section, but the cross-validation that was compared were for the highest prediction accuracy, the lowest bias, and the lowest worst case error using the different statistics in the tool. They were all given an equal weight, and at the end, the highest ranked model was the ordinary Kriging optimized model. So after I had the best performing model, I needed to generate the geostatistical layers to compare the cross-validation statistics. This was a bit troublesome because it turned out the optimized model was the best performing, which wasn't available using the standard Kriging geoprocessing tool. It required using the geostatistical wizard to generate those, since there's a button you need to click in there to optimize the semi-variogram. And so this was, in order to kind of speed this up and make sure I wasn't making mistakes with the multiple button clicks that you have to do in the wizard, I was able to save the model as an XML file, modify the flags within that XML file to re-optimize the model every time it was run, and then input that into the Create Geostatistical Layers tool to run all of the individual 45 days for the geostatistical layers. So by using the XML file, I was able to reduce the potential for error of clicking through the statistical wizard for all of the 45 different files. Next was to compare the cross-validation statistics from those layers. And so I used the Compare Geostatistical Layers geoprocessing tool. The comparison method you can see on the right used different criterion. And so since the Kriging was the one that was used, I had more cross-validation statistics to evaluate. And so I was able to look at things such as the highest prediction accuracy all the way down to highest precision for this. And we'll go a little bit more into this when I get to the results section. After that, I had the geostatistical layers, but I needed to turn them into an animated map series. And so I used two different models here. So the first was to turn the geostatistical layers into contours. And so I developed a model to iterate over the 45 different layers and generate contours for those. For the class breaks for the contours, I used the EPA's air quality index breakpoints for PM2.5 concentrations. You can see those in the bottom left-hand corner for the table. That takes PM2.5 concentrations and buckets them into categories that the general public can understand. Most people don't generally understand what a particular concentration means for their health. So this takes those different concentrations and buckets them into categories such as good all the way down to hazardous. After I had that, I also generated an air quality index style model to iterate over those 45 different contours and apply the styling that you see in that category column. And so the output of this was 45 different feature layers with the EPA PM2.5 AQI symbology applied to them. Lastly, I wanted to generate an animation of these. So I used the thematic map series function in ArcGIS to develop consistent layouts for all the 45 different days, which were then exported to JPEGs and then imported into Adobe Photoshop, where I used the timeline feature to create animated GIFs of each of the 15-day study periods. So circling back to the results, so the first was the results of the exploratory interpolation. And as I alluded to, the best performing model was the ordinary Kriging optimized model. So what the numbers you're looking at here are the rank based off of the cross-validation criteria, which were highest prediction accuracy, lowest bias, and lowest worst case error. And of all of these different interpolation models, the best performing for all three scenarios turned out to be the ordinary Kriging optimized. And so at the end, averaged together, the highest average ranked model was this, and which was why it was used for this study. For the comparison of the geostatistical layers tool, as I mentioned, there was 5 different criteria that were evaluated, and each of these were given an equal weight, so a weight of 1. And you can see in the second column there is the cross-validation statistic that was evaluated. So things such as mean error, root mean square error, maximum absolute error, average standard error, and root mean square standardized error. And the number you're seeing next to it is its rank based off of those. So you'll see they each achieved various ranks for different criteria. And at the end, averaged over those 5, the average rank turned out to be a tie. So for the monitors and corrected air sensors, they turned out to have a tied average rank of 1.8. The monitors and uncorrected air sensors didn't perform quite as well and had an average rank of 2.4. So what you're going to see on this screen, oh, there it goes. So hopefully what you can see here, this is the output of the Adobe Photoshop animation. So this is for the monitors and corrected sensor data. So what this does is it iterates at a 1-second pace over each of the interpolation surfaces to show where the air pollution is proceeding throughout the 15-day study period. So as you'll see right now, we're getting closer to the holidays. So when everyone lights up their fireplaces and set off their fireworks, the air quality gets substantially worse. And so this map kind of correlates with those and kind of demonstrates the spread of the pollution over the valley using the sensors and the monitoring data. So in conclusion, the highest ranked model was the ordinary Kriging optimized model. The highest ranked data scenarios were the monitors and corrected air sensors scenarios. And through this, different models and workflows that were generated, which hopefully will allow people to duplicate this study in other locations. Some suggestions for future studies are identification of regions with greater numbers of data points to leverage more interpolation models. So due to the limited number of data points, only certain interpolation models were able to be used. Duplicating the study over a period with less variability. So this time period was selected due to its variability to show differences in the concentrations. However, you might get different results if you picked a study period with less variability. And also, further study could be used on verifying the locations of these public air sensors. So these air sensors don't have GPS units in them, so the locations of the sensors are all just user inputted. So further study on methods for verifying these air sensor locations could allow them to be used in more regulatory purposes. I have my image credits here, and I'm happy to take any questions, and thank you for the opportunity.